Hello students, in this lecture we are going to consolidate our knowledge on fundamental identities of trigonometric ratio. As we all know this right angle triangle and the kind of relation their side does share, we end up getting all of six trigonometric ratios. For example, sine theta, which is the result of opposite over hypotenuse, cosine is said to be adjacent over hypotenuse, tan is said to be opposite over adjacent, so on and so forth. And if I use Pythagoras theorem, then we end up getting these three fundamental identities, which I'm sure each one of you do know. But when it comes to apply this identity in equation application part, if it is concerned, then maybe we failed miserably. In this lecture, we are going to cover up a bunch of questions based on these fundamental identities. So without any further ado, let's get started. The first one, it's a reduction of sine 4 plus cosine 4. And the second one, it is sine 6 plus cosine 6. I would recommend you to just not only to check how would we prove this expression, but you should remember this one because JEE has asked question based on this relation directly, and not only for trigonometric point of view but for calculus point of view. This relation, it does it is something which we are going to use directly. So regarding sine plus sine to the power 4 theta plus cosine to the power 4 theta, I am going to apply this identity or this algebraic formula that I can write a to the power 4 plus b to the power 4 in a square plus b square whole square minus 2 times of a square b square. So now the real question is that why I'm using this identity. Very pretty reason is that I know a relation in a square plus b square which eventually become a 1. So if I try to square this a square plus b square further, I know there will be a term of a to the power 4 plus b to the power 4 which will help me to reduce this expression or convert into product of two trigonometric terms. So let's just replace this a square plus b square with 1 minus 2 times a square stand for sine square theta times b square, it is cosine square theta. There we go. Similarly, if you look at the second one, so rather than reading this expression as something to the power 6, I would advise you to read this one as a sine square theta whole to the power 3 plus cosine square theta whole to the power 3. Now you are free to apply what a cube plus b cube stand for. It is a plus b, which will give you a 1, then a square plus b square, that is sine to the power 4 theta plus cosine to the power 4 theta minus a square b square. Now sine to the power 4 plus cosine to the power 4 is something which we have already derived. So put the value of this expression there. There you go. You will end up getting a relation. It is 1 minus 3 sine square theta cosine square theta. Question like this FK in format of FK has been asked in JEE. You need to find 3 times F4 minus 2 times F6, where F4 and F6 is nothing but this relation which we have simplified in terms of sine square theta into cosine square theta. This is the one of the reason why I ask you to remember this to result by heart. It will not only say save you a lots of your time, but it will enhance your calculation. Now in the next one, we need to prove this relation square root of 1 minus cosine over square root of 1 plus cosine. No need to tell you this time that removing irrationalities from the denominator is what we are looking for. So in that case, you need to multiply and divide the whole expression by 1 minus cosine theta. The moment you do that, you'll get your answer in terms of cosecant as well as a cot. Now in the next one, secant to the power secant square a plus cosecant square a whole square root. We need to prove that this is equals to tan a plus cot a. Now secant square a will help us to replace or to express this term in terms of a tangent, because in tangent in cos tangent is what we are looking for. So without wasting your time, just put or replace secant square a. It is nothing but 1 plus tan square a. Similarly, cosecant square a is tan for 1 plus cotangent square a whole square root. Now try to read this expression. Try to read this expression as a square, which is tan a whole square, b square, which is cotangent a whole square plus 2ab. Since 2ab is nothing but a 2 times tan A times cot A, but there isn't any term of tan A into cot A there. Since tan A into cot A will give you a 1, and this will help you to understand that this expression is nothing but a square of tan A plus cot A. And once you take the square root of square of tan A plus cot A, you will get the result. You don't have to worry about the sign symbol, because here A is something which is lying in the quadrant number 1, where both the angle will be positive. In the next one, we have all 6 trigonometric functions are there. We need to prove that this expression is equals to 1. Whensoever we have multiple trigonometric function involved in a single question, try to go with your flow. Try to convert is the particular function according to your comfort. I feel comfort in sine compared to cosine, cosecant. So I'll be replacing cosecant A with 1 over sine A. Then sine A will remain as it is. In the second one, secant A, I'll try to write this secant in terms of cosecant A, since both are reciprocal to each other. So there you go. Wherever tan A plus cot A is something which will give you 1 over sine A times cosine A. By that manner, I have converted each and every term in sine and cosine. Now there we go. In numerator, we have 1 minus sine square A, which is nothing but cosine square A over sine A times the next one will become 1 minus cosine square A, which is nothing but square of sine A over cosine A times we have further 1 over sine A times cosine A. As you can see, we have 2 times sine A, 2 times cosine A in numerator as well as in denominator. We end up getting a result equals to 1. Now, in the next one, we need to prove this identity. This is something where we used to use, where we have to be a bit creative. First, there are multiple ways to solve this identity. Either you may go with the multiple and some multiple angle, but if you want to interact with all these 3 fundamental identities, then you have to replace any one of the one from numerator or even from a denominator. Now, the real question is, what can I write instead of a 1? So you just need to fit any of the fundamental identity there. Since the term of tan and secant are there, so rather than using or replacing one with some other trigonometric identities, try to replace this one with secant square A minus tan square is, isn't it? So what will I get if I replace one with secant square A minus tan square A? Now you can see in the numerator that we can take out tan A plus secant as a common. So the moment you are taking tan A plus secant as a common, we end up getting a 1 minus secant A plus tan A. Am I right? And in denominator, we have a similar term as of this one of the factor in numerator. It is tan A minus secant A plus 1. In result, this similar or identical factor will get cancelled out. And the way, in the moment I convert the term of tan and secant in sine and cos, I'll end up getting the result as of 1 plus sine A over cosine A. All right, so I'm sure you come to know. All right, so we have one more question before we end this session. Secant A plus tan A, if it is equals to 2, how can I find out the value of sine theta? So now you don't have to convert this expression into sine and cosine this time. You just have to recall your one of the identity which correlates secant and tangent in a one in a one equation. As we know that secant square A minus tan square A is something which is equals to 1. And by that way, if I try to factorize using A square minus B square, I can say that whatever value of secant A minus tan A hold, it will be equals to the value of 1 upon secant A plus tan A, because both are reciprocal to each other. I already know the value of secant A plus tan theta. Excuse me, here argument is equals to theta. This is something equals to 2. So can I write the value of secant theta minus tan theta will be equals to 1 over 2. If I try to add this expression, I'll end up getting the value of 2 secant theta. It is equals to 5 over 2. There we go. Once we get the value of secant theta, it is equals to 5 by 4. That means we know the value of cosine theta, that is 4 over 4, and it will attract two different outputs for sine theta. If I use the first trigonometric identity is there, Sin theta will be either positive 3 by 5 or negative 3 by 5. But since it is given that angle is acute angle, so we have to settle ourselves with the one response only. So there we go. Sin theta equals to 3 by 5 will be our response. And the last one, 3 secant to the power 4. It's a biquadratic equation in secant squared theta. You don't have to worry anything about. Just replace your secant squared theta with some other variable. The moment you do that, you have a quadratic equation in that particular variable. And now it's time to factorize this equation. So let me write down its factor. It is 6 and 4 will be there, plus 8 will be equals to 0. From there, two different values of p will have two different values of p. One which is where p is equals to 4 by 3, and another one where p will take the value equals to 2. But p, it is the value of secant squared theta. So once I know the value of secant squared theta, I think it is a piece of a cake to know the value of tan theta from there, isn't it? Since we know secant square is 1 plus tan squared theta, from there we end up getting tan squared theta will be either equals to 1 by 3, or we may write tan squared theta will be equals to 1. Since again theta is your acute angles, only a single value will be acceptable. I'm sure you like this video. So that is fellows for this lecture. Thank you very much.